In a previous DSP morsel, we designed a reduced delay FIR filter. We used 41 coefficients to meet this specification that's shown here, and the hard part of that, and required some handcrafting, was the 13.8 samples of group delay across its passband, extending from DC out to 0.2 normalized frequency. The issue now is, can we take that FIR filter, use it as a prototype, and make an IIR filter which will be a more economical realization? Well, first let me load in those coefficients that we did on the previous occasion. It's called H of K, and bring this in from the workspace. I'm going to import guest filter called H of K. In it comes, this advises me that I've got 41 coefficients, so I might as well make this 41 in the right hand corner, and I might as well look at things in absolute gain terms, not dB, absolute gain terms, and furthermore get rid of frequency sampling so that I've only got just my previous design. I recognize it. I'd noticed that in fact its impulse response is peaking up to the left of center here, obviously indicating a reduced delay situation. The question is, will Brandenstein, that is to say Brandenstein-Unbehauen, be able to do as good a job? Well, this is an excellent algorithm. We'll click it on and have it hooked to the guest filter, and it's having no trouble whatsoever because we're expending 29th order approximation, which is way too much. Let's give it less horsepower. It drops down to 9th order. Not quite a good enough hug on this. I don't like it visually, so I'll bump it up to 10th order, and visually it's a very nice fit indeed. It would be nice if this turned out to be the final design, because we'd only have, roughly speaking, 10 in the numerator, 10 in the denominator, about 20 multipliers, as opposed to the 41-ish which are involved in the original filter design. Let's have a look at these together. Two filters to look at. Bring it over here, and the important thing is to look at the group delay. Of course, overshooting as is customary. 14 will be my upper edge, 13.6 samples here, and let me toggle in so that I'm looking just at the guest. Here I see my 13.8 target, and I'm easily within this corridor plus or minus 0.1 all the way out, in fact beyond 0.2. This is a very good design. I'm very happy about that. Let me toggle to the Brandenstein approximation. Not quite so good. In fact, it pokes out of our corridor even back here, so I don't have enough approximation order, and so I'm going to increase this now to 11 and see what will happen to me then. I'll bring this back up so I can see what's happened. And now, sure enough, Brandenstein is pulled in very nicely. You can see that it's easily within all the way out to here. So this group delay situation is now all right. I'll get rid of that picture, and I'll ask the question, have we met the specification in terms of magnitude? Well, let me just remind myself about what those specs were, and then go and call up a quality measure on this filter. I'm going to look at my Brandenstein one, bring it up, and see what it's telling me, and remind myself again. So it said that we've got to be cutting off around about 0.2. Yes, of course we are. We wanted to have a passband ripple of less than 0.02. Well, here it is, 0.01, easily in. Transition width, 0.1 or less, it's just in nicely. And then finally we wanted to have stop band attenuation no more than at least 40 dB, and so we've made 49 dB. All in all then, we've met our specification quite handily. We've done it with 11th order Brandenstein-Unbehauen, and this now means we've saved quite enormously, almost a factor of 2 on our multipliers. Successful design.